Okay, this is our first unit for AP Chem, and we build our course around the big idea. So Unit 1 is based on Big Idea 1, and it includes electron structure and atoms, which is Chapter 6 in the book, and it includes periodic trends, which is Chapter 7. Okay, and if you look at Big Idea 1, it basically says three things. One is that the elements are fundamental building materials of matter. I think we would all agree with that. That matter can be understood in terms of the arrangements of atoms, right? So it's about how they're arranged, it determines their properties and how they react. And those atoms retain their identity in chemical reactions. And get started on electromagnetic radiation. And if you are interested in reading this in the textbook, you can follow along in the textbook, the Brown and LeMay textbook, section 6.1 through 6.4. Okay, so in order to talk about electrons, we have to first talk about the electromagnetic radiation, and in order to understand radiation, we have to understand waves. So when we talk about a wave, just like a wave at the ocean, we can describe the wave as having a wavelength. It would be the distance from one crest to one crest, or one trough to one trough, or one section here to one section here, okay? Wavelength is pretty easy. Amplitude is the height of the wave, although we don't typically use that. Okay, frequency is a little bit more complicated. Frequency is how many waves go by in a set amount of time. Okay, so if we think about this and we were to plot the waves going by, and we measured that as a function of time, we can, and time is almost always plotted in seconds when we're talking about waves. We can look at how many waves go by in a certain amount of time. So if I look at how many waves go by in 1 second, which is usually the length of time I'm talking about, I can look at it and say if I'm starting right here in the wave, this would make 1 wave and this would make 2 waves. I have 2 waves per second, right? And so what I would say is I have 2 hertz. Hertz means some number per second, okay? So either I would say I have 2 hertz, or I would say 2 to the second minus 1, which is the same thing as 2 over seconds. All right, so take a minute and determine what the frequency of this wave would be. Okay, so I've got to orient myself. There's my 0. There's my 1 second. I got to see how many waves cross in that amount of time. Here's 1, 2, 3, 4, and 5. So my frequency is 5 hertz, or 5 to the seconds minus 1, or 5 over seconds. Okay. Okay, so we can look at the electromagnetic radiation. We can see some waves, and those that we see we call the visible spectrum, the visible region of the electromagnetic spectrum. But it's actually a very small part of the whole range of what exists. And if you have this picture in your textbook, and on the left here we have gamma rays, and on the right we have radio waves. And these radio waves are huge, lumbering waves. If you think about it, they're waves sent over by the radio, larger than football fields. Sometimes they can be as large as a meter or more, right? And then on the other side, we have gamma rays, which are very high frequency, very high energy, damaging rays, okay? And this little section right here is the visible section, the visible region, which is just from 400 nanometers to 750 nanometers, okay? And you do need to know that 1 nanometer is 1 times 10 to the minus 9 meters. Now the other thing you need to know is sort of the relative energies or wavelengths of the different regions. You got to know gammas are the strong ones. They come out of nuclear reactors. Radios are those big, long ones, right? I think it's easy to think about what happens in a infrared and ultraviolet by thinking about what we know about Bunsen burner flames, right? So if I have a red or yellow flame, that's a cooler flame, And if I have a blue or violet, that's going to be a really hot flame. And hot suggests really high energy, right? High frequency, as this would be lower frequency. So this is the red area, and this is the violet area. So red is cooler. It's near the infrared. So they're going to be even longer than the red, than the visible. And the ultraviolet are going to be in the higher energy. They're closer to the violet, higher in energy. Okay, so the other thing we have to be a little bit careful of is that you can't rely on what's on the right-hand side and what's on the left-hand side, because there's many tables, electromagnetic spectrum tables, that show gamma rays on the left. There are just as many that show it on the right. So you need to get yourself oriented. The blue side of the visible is the hotter or more energetic side. The red is the cooler side. Gamma rays are over here on the hot side, right? Okay. And hopefully you're getting the appreciation that the longer the waves, so the higher the wavelength, lambda is the symbol that we use, the lower is the frequency, and we use the symbol nu. Okay? So as one doubles, the other halves. As it turns out, all electromagnetic radiation, doesn't matter whether it's gamma rays or radio waves or yellow light, moves at the same velocity. And that velocity you need to know, actually it's on your equation sheet, is 3 times 10 to the 8 meters per second. And the symbol that's used for that is a lowercase c. Now, one of the relationships that is also on your equation sheet that we will use is that the speed of light is equal to the wavelength times the frequency. Very useful equation. If we know any two of those, we can figure out the third. Okay, and of course we always know the speed, right? We always know what c is. So if we know wavelength, we can figure out frequency and vice versa. Okay, so here's a question. Give it some thought. Go ahead and answer it. What's the difference between visible light and electromagnetic radiation? Because visible light is just one part of the electromagnetic radiation. All visible light is electromagnetic radiation, but not all electromagnetic radiation is visible light. Okay, here's another. Human skin is not penetrated by visible light, but it is penetrated by X-rays. Which travels faster, visible light or X-rays? So pause it. Both visible light and X-rays travel at the same speed. All light travels at the same speed. Times 10 to the 8 meters per second, which is also 186,000 miles per second. Very fast. All right, here's another one for you to think about. 2 electromagnetic waves are represented in the image below. Which wave has the higher frequency? Okay, so higher frequency is which one comes along more often, right? So that's going to be this one. If one wave represents visible light and the other wave represents infrared radiation, which wave is which? Okay, visible light, remember it's the red to violet. Red is the cooler side. Infrared is near red. So infrared is going to be longer wavelengths, right? So it's going to be, that would be the infrared, and that would be the visible. Okay, so one of the things that Max Planck was studying was if you heat up an object, it will often glow, especially metal, right? We've seen this. We throw something into the fire and we see it glow. Sometimes it'll glow red or glow yellow, sometimes even green, depending on what it is. And depending on how hot it is, it glows different colors, just like we were talking about the Bunsen burner flame. And so one of the things the scientists were stumped by was that they could not explain this glow using what we knew about waves. So Planck came with the idea that there must be some particle nature of matter, of waves or light that is not, that's a little bit different than the way waves behave. So we say electrons have wave-particle duality, that they have some behavior that's like waves and some behavior that's like particles. What Planck said was that energy comes in these packets called quanta. If you think about quanta, think about a quantum leap. I make a quantum leap, I got to jump to a certain level before I can get up to where I'm going. Okay. All right, so Einstein fed off the work that Planck did, and what Einstein did was he looked at this photoelectric effect. And the photoelectric effect is really what Planck was talking about. Planck and Einstein both were talking about. Okay. Okay, so this is what Planck and Einstein were talking about, the photoelectric effect. What happens if I take a piece of metal, let's say any kind of metal, and I have its surface exposed, and I apply radiation to it, that light gets emitted. And I can devise a device that is able to read the current at which this electrons come off. Okay? And so what Planck said and what Einstein said is the energy, there's distinct levels of energy, and there has to be enough energy to come off to cause these electrons to come off. That it's not all or nothing. Okay? And Bohr went a little further, making this clearer for us. Okay, so what Einstein said was that E equals h nu. The energy of this photon or this electron coming off as colored light, which he's describing like a packet or a particle, is equal to some constant, which is now called Planck's constant, times nu. Okay, so if I give an object a certain amount of energy of a certain frequency, I can cause an electron to come off. It's got to be high enough. Okay, if I want more electrons to come off, I need to give it another whole packet. So I need another higher frequency to get the second and third and subsequent electrons or photons to come off. Okay, so we're given this problem here. We want to calculate the energy of, so we're trying to find energy of one photon of yellow light whose wavelength is 589 nanometers. Okay, so I'm trying to find energy. If I look at my equation sheet, I'll see that I have some useful information there. I have the two equations we've been talking about, E equals h nu, and I also have some useful constants that I can use to answer this problem. So I'm given the wavelength, right? I know lambda is 589 nanometers. I'm trying to find energy. The equation for energy is h nu, right? I know Planck's constant, but I do not know frequency, so I have to find frequency first. So to do that, I'm going to use the other equation, C equals lambda nu. And in order to get frequency, I rearrange the equation and I get C over lambda. Now, one of the things I have to be careful about here is if I look at the speed of light, it's given in meters per second. But what I have here, my length units here are nanometers. So I have to convert one to the other. And one of the things, like I said earlier, you need to know, 1 nanometers equals 1 times 10 to the minus 9 meters. Okay, so I'm going to use meters in this. So this is 3 times 10 to the 8th meters per second over, I'm just going to say 589 times 10 to the minus 9 meters. Okay. When I do this, my meters are going to cancel out, and I'm going to end up with, let's go ahead and punch that. I get, now I want to leave the numbers in my calculator. That's the best thing to do from a sig fig standpoint, but if I want to write something down in the meantime, I can do that. And that's going to be seconds to the minus 1, right? Alright, so that gives me my frequency, and now I can use this equation. So if I do that, my energy is h nu. My Planck's constant is given to me at 6.626 times 10 to the minus 34 joules second. And then here's my frequency, 5.093 times 10 to the minus 14s. And that's over seconds, right? So my seconds are going to cancel out. And if I multiply those out, I'm going to get 3.37 times 10 to the minus 9 joules. Okay? And you know what? That looks like a really tiny number. But don't forget, I am just talking about one photon. If I wanted to know for a mole of photons, you know, I could multiply this number times Avogadro's number. And when I do that, I end up with 2 times 10 to the 5 joules. Wasn't asked that for that in the question, but it's a much bigger number when I'm talking about a reasonable sample. Okay. Okay, so suppose we have yellow light can be used to eject electrons from a certain metal surface. What would happen if we use ultraviolet again? Okay, electrons will still be ejected, but they're going to have greater energy coming off. One good way to identify how much energy something has been subjected to is to determine how much energy it comes off as. Okay, we're going to see that again and again. Okay, so one of the other things that was stumping scientists was that we've seen these in the lab, these spectrum tubes. They have gases of atoms and sometimes compounds, and if we expose them to high energy, they glow. Okay, and what surprised scientists is if you were to take that material and you looked at it through a prism, that you would get this continuous spectrum like a rainbow. Okay? That's what they expected. You see a rainbow in the sky, you see a full spectrum rainbow. Okay. But what they actually saw when they looked through these energized gases is just these thin little lines. Depending on what the element is, they would see these thin little lines. And they were trying to explain why these little lines and not the rainbow. Okay, and that led to Bohr's explanation. Okay, and this is what Bohr said. He took off the work that Planck and Einstein and everybody else did. And what he said was, when an electron gets energized, it moves from its ground state, where it is before being energized, to its excited state. It can get excited to 1 level or 2 level or 3 level. And that eventually that energy has to go somewhere, and it happens almost immediately. And what happens is when that electron comes back to its ground state, it emits light, colored light. Okay? And he said that depending on where that electron is to start and how far it has gone up, and therefore how far it has to go back and how much energy is being released, will determine the color of the light. Okay? But it can only happen in these discrete areas, some of which are visible, we'll see the lines, and some of which might be in the ultraviolet region or the infrared region. Okay, so what he said is if I have a big jump like this, when I go back, I might see blue light. But if I had, let's say, an electron that went from this energy level to this energy level and back, I'm going to see that as red light because it's a lower energy, lower frequency wave. Okay. So what Bohr said was, because what happens is I only get these discrete color lines coming off, that electrons must only be located in these very specific areas around the nucleus. Okay? And that's how you got Bohr's model, where he had specific energy levels, and he said that's where the electrons can exist. They can exist in these specific energy levels, but they cannot exist in between. And he said also, of course, that the energy levels are like the rungs of a ladder. If you have enough energy, you might be able to get to the first step. Okay? If you have a little bit more energy, you might be able to get somewhere in between, but you're not going to land in between two steps. You have to have another quantum of energy, another quantum or packet of energy to get to the next step. Okay. All right, so this is what Bohr's model looked like. He said that depending on how far away from the nucleus, let's say this is the nucleus, this is the first shell, second shell, third shell, depending on where the electron is and how high it gets energized and then how far it comes back, the greater the difference in energy, the higher the frequency of that color. Short transitions are much shorter. Okay, so we're going to stop right there.